Dear students, today we'll see some multiple choice questions on the topic semiconductor electronics. So here, these questions are useful in our competitive exams like NEET, JEE, and CET. So let's start with the questions. Question number 1. Electrical or conduction in a semiconductor takes place due to which of the option is correct? Electrons only, holes only, both electrons and holes, neither electrons nor holes. Now, when we have studied semiconductors and when we saw the atomic structure, we saw that the charge carriers were the electrons. And whenever electrons move from one place to another, the vacant place of an electron is considered as hole. And in semiconductor, we consider both electrons and holes as charge carriers. These are the carriers which carry electric current from one point to another. So it is both electrons and holes which are used for electrical conduction in semiconductor. So here if you see the explanation, a semiconductor has two types of charge carriers, that is holes and electrons. The conductivity of a semiconductor is sum of conductivities of holes and electrons. So here option C, that is both holes and electrons, is the correct answer. That is, electrical conduction in a semiconductor takes place due to both electrons and holes. Then we'll go to the next question. Silicon is a semiconductor if a small amount of As, that is arsenic, is added to it, then its electrical conductivity, that is its ability to make electric current flow, what will happen to that? So we'll see the options. The options are A decreases, B increases, C remains unchanged, and D becomes 0. Now, when we speak about silicon, silicon is a pure semiconductor. And we know in a pure semiconductor, the number of excited electrons is equal to number of holes. And therefore, only if a temperature increases, covalent bonds can break and electrons can become free. And then we can have certain charge carriers for our electrical conduction. But the other method, that is to increase the conductivity of a pure semiconductor, is doping. Now, in this question, if a small amount of As, that is arsenic, is added to a pure semiconductor, say silicon, then its electrical conductivity, what will happen to its electrical conductivity? So if you see this addition of this impurity like arsenic, say this is an arsenic atom. If you are having this as arsenic atom, now arsenic atom is a pentavalent atom, so it's a pentavalent element. That means it has 5 valence electrons. So we can have one valence electron here, one valence electron here, one valence electron here, one valence electron here. And now when it gets combined with silicon, so silicon atom is here, say this is silicon, silicon atom is here also, this is silicon, silicon atom is here, silicon, and silicon atom is here, silicon. So silicon will have 4 valence electrons. It is a tetravalent element. So here you can show its 4 valence electrons, 1 2 3 4. Here you can show 4 valence electrons, 1 2 3 4. Even here you can show 4 valence electrons, 1 2 3 4. And even here you can show 4 valence electrons. Now if you concentrate on the arsenic, now arsenic is a pentavalent element, so it will be having 5 valence electrons. Out of those 5, 4 will make covalence bond with its neighboring silicon atom, and 1 electron will remain extra. So there will be 1 free electron whenever a single atom gets added to a silicon set. So here, if you add a small impurity of arsenic, there will be many such free electrons available, and it gives rise to an N-type semiconductor. Now, as this question is concerned, if a small amount of air, that is arsenic, is added to it, then its electrical conductivity will increase because you're increasing the number of electrons. So option B will be the right answer here. So here the impurity increases the conductivity of a pure semiconductor. Hence, if a small amount of arsenic is added to silicon, then its electrical conductivity increases. So here option B, that is increases, will be the right answer. Then we'll go to the next question. Question number 3. When the electrical conductivity of a semiconductor is due to the breaking of its covalent bonds, then the semiconductor is said to be. Now here we are speaking about the basic pure semiconductor, because here we are not adding any impurity. Here we are not doing any other arrangement to increase the electrical conductivity. Now here, just by the rise of temperature, if some covalent bonds break and therefore you get certain free electrons, then there will be electrical conductivity. If this is happening, then it is a pure semiconductor. There is nothing added to it. So a pure semiconductor is also called as intrinsic semiconductor. So out of these 4 options, option C will be the right answer. When the electrical conductivity of a semiconductor is due to the breaking of its covalent bonds, then the semiconductor is said to be intrinsic semiconductor. So here, the electrical conductivity of a semiconductor is due to the breaking of its covalent bonds. This means that the semiconductor does not have any charge carriers of its own in the beginning. This is true for intrinsic semiconductors, as the atoms in it have their octet completed and therefore lack of any free electrons. So here option C will be the right answer, that is intrinsic semiconductor. Then we'll go to the next question. The mobility of free electron is greater than that of free holes because the options are: they are carry negative charge, they are heavy, they are mutually colliding less, they require low energy to continue their motion. Now, out of these 4 options, option D will be the correct answer, that is, they require low energy to continue their motion because the masses of free electron, the mass of free electron is always less than the mass of holes. So the energy required to move an electron, the mobility of electron, is less. So it requires low energy to continue the motion, and therefore the mobility, that is moving of free electron, is greater than that of free holes. So option D will be the right answer here. So here you can see the reasoning. The electron effective mass is often smaller than the hole effective mass. This is one basic reason. Electron mobility is often greater than hole mobility. Electrons need less energy to move because they encounter less resistance during their motion than holes. So it is the less energy required to move an electron that makes the electron mobility greater than the hole mobility. So here you can see option D is the right answer, that electrons require low energy to continue their motion. Then we'll go to the next question. Question number 5. Carbon, silicon, and germanium have 4 valence electrons each. At room temperature, which one of the following statements is most appropriate? That is, which one of the following statement is correct? So the statements are: A, the number of free conduction electrons is negligible small in all the 3. B, the number of free electrons for conduction is significant in all the 3. C, the number of free electrons for conduction is significant in C but small in silicon and germanium. D, the number of free electrons for conduction is significant only in silicon and germanium but small in C. Now, if you see these elements, carbon, silicon, and germanium are semiconductors, and carbon is a non-metal. Therefore, it is obvious that the number of free electrons for conduction is significant only in silicon and germanium, and it is very small in the carbon. So option D will be the right answer here. So here, since a carbon is non-metal while silicon and germanium are semiconductor, hence at room temperature, free electron for conduction is significant for silicon and germanium but negligible in carbon. So here option D is the right answer. Then we'll go to the next question. Question number 6. Which circuit will not show a current in ammeter? So if you see this circuit, in this circuit, this is a voltage supply given. This is the positive potential. This is the negative potential. So here positive potential is connected to the cathode of diode, and negative potential comes to the anode of this hot diode. And here you can see this diode will be like forward bias, but the first diode is like reverse bias. So here there will be no current flowing here, no current flowing. So this ammeter will not show any current. So option A will be the right answer, but we will see option B, C, and D again. So in option B, if you see this positive potential, negative potential, positive is given to the anode and negative to the cathode. So this diode is forward bias. This diode also is forward bias. So current is going to flow, ammeter will show the current flowing. Now even here, if you see positive potential, negative potential, positive is given to this anode also, and negative is given to this cathode and to this cathode. So both the diodes are forward bias, both are going to conduct, and there will be a current flowing here. So ammeter will show the current flowing. Even here, if you see, this is positive potential, this is negative potential. So this diode is forward bias, and this diode will make the flow of current to go like this, and the ammeter will show the flow of current. So out of these options, the option A, as I've told you earlier, will not show any current because the first diode is reverse biased and there will be no flow of current, and therefore the ammeter will not show any current through it. So here you can see option A is the right answer. Then we'll go to the next question. Question number 7. Consider the junction diode is ideal. The value of the current through the resistance of 300 ohms. How much is the value of the current through the resistance? 300 ohms. So here options are 0.001 ampere, 0.1 ampere, 0.01 ampere, and 0. Now if you see the arrangement of the circuit, so here we have a minus 4 volt. This is minus 4 volt, and here we have minus 1 volt. So the magnitude of voltage at the anode, this is the anode of the diode and this is the cathode of the diode. So magnitude of the voltage at the anode, that is minus 4, is less than, or is less positive than the magnitude of voltage at the cathode. So anode is negative with respect to cathode. So the voltage at anode is less positive as compared to cathode. Therefore, this diode will be reverse bias, and therefore no current will flow through it. So here, out of these 4 options, the value of current through the 300 ohm resistor, that is this current, so there will be no current flowing, so the value will be 0. So option D will be the right answer here, that is 0. So here you can see option D is the correct answer. Then we'll go to the next question. A full wave rectifier circuit along with input and output are shown in the figure. The contribution from diode D2 is, or are, options are only C, option B is BD, option C is AC, option D is ABCD. So here if you see, this is the input waveform. So here we can have positive half cycle, negative half cycle, positive half cycle, negative half cycle. If you see this circuit, whenever the input is positive half cycle, this point is positive and this point is negative. So the first diode will conduct and the output will get its voltage because of the first diode. So this A will go because of diode D1. Similarly, when the input is negative, this point becomes positive and this point becomes negative. In that case, diode D2 will conduct and the output will get voltage because of D2. So the second half cycle at the output is because of diode D2. Similarly, for the third positive half cycle, again the top point will get positive and the down point will be negative. So the first diode will conduct and the output is because of D1. Similarly, again when the input is negative half cycle, the second diode will work and the output is because of D2. So if you speak a contribution of D2, then the output which is arising because of D2, that is the second diode, is B and D. So here B and D are the right answer. So here option B is the correct answer, that is BD. So here you can see option B is the right answer. Then we'll go to the next question. Question number 9 says that a PN photodiode is made of a material with a band gap of 2 electron volt. The minimum frequency of the radiation that can be absorbed by the material is nearly how much? So the options are 1 into 10 to the power of 14 hertz, 20 into 10 to the power of 14 hertz, 5 into 10 to the power of 14 hertz, 10 into 10 to the power of 14 hertz. So here we know that our band gap energy is 2 electron volt. So we can take Eg is equal to 2 electron volt. Now the wavelength is given as, wavelength lambda is given as Planck's constant multiplied by velocity of light upon band gap energy. This is nothing but 1240 electron volt nanometer upon 2 electron volt. Now this lambda will become 1240 upon 2 is nothing but 620. So 620 nanometer. So this is nothing but 620 into 10 to the power of minus 9 meter. Now if we have to calculate what is the frequency, so frequency will be given as velocity of light upon lambda, that is the wavelength. Velocity of light is nothing but 3 into 10 to the power of 8 meters per second upon lambda is nothing but what we have calculated earlier is 620 into 10 to the power of 9 meters. So if you solve this, you will get F is equal to approximately 5 into 10 to the power of 14 hertz. Okay, now this is the answer. So here option C will be the right answer here. That is 5 into 10 to the power of 14 hertz. So here you can see option C is the right answer. Then we'll go to next question, question number 10. In the energy band diagram of a material shown below, the open circles and the filled circles denote holes and electrons respectively. The material is what? So the options are a p-type semiconductor, n-type semiconductor, insulator, and metal. So here if you see this energy band diagram, so here this is the valence band. Now in valence band you can see many holes. These all are holes. So there are many number of holes. And in a conduction band, this is a conduction band, you see a very few number of electrons. So the material in which there are large number of holes and few number of electrons, so holes are acting as the majority charge carriers, it is a p-type semiconductor. So here in this band diagram, number of holes in valence band are more as compared to number of electrons in the conduction band. So it is a p-type semiconductor. So here option A is the right answer, that is p-type semiconductor. Thank you, students.